The human mouth functions as a continuous, microscopic battleground. The surface of your teeth is locked in a conflict with billions of foreign bacteria. When you eat carbohydrates, especially sugars and starches, those bacteria feed on the residue. As they digest those sugars, they produce a highly corrosive acid as a byproduct. This acid attacks the hard outer layer of the tooth, stripping the enamel of essential calcium and phosphate. This is demineralization, a process that physically weakens the surface and often leaves faint white spots where the structure has begun to fail. At this early stage, the damage can be repaired. Saliva acts as a mineral delivery system, carrying calcium and fluoride back to the weakened enamel to plug those microscopic gaps. Tooth decay is a slow, measurable war of attrition. Biology can win this fight and repair the damage, provided the acid attacks are stopped and the minerals are replenished before the structure collapses. If the acid attacks are too frequent, the saliva cannot keep pace. The outer defenses are eventually overwhelmed, and the weakened enamel structure collapses entirely. This collapse creates a physical breach, a cavity. What was once a solid protective barrier has become an open sinkhole, hollowing out the tooth from the inside. Once a cavity is open, bacteria migrate into the void, pushing toward the sensitive nerve center of the tooth. Without treatment, this leads to intense sensitivity, chronic pain, and eventually the death of the tooth. At this point, the tooth has suffered a structural failure that the body cannot reverse. Enamel does not grow back. The only way to save the tooth is through an engineered intervention. To fix the damage, the dentist must first act as a demolition expert. Before they can rebuild, they have to remove the contaminated material. Under local anesthesia, the dentist uses a high-speed drill to clear out the mushy, bacteria-ridden tissue. The goal is to strip the tooth back to its clean, healthy walls. This process halts the infection, but it leaves the patient with a clean, sterilized, and completely empty hole inside their tooth. Rebuilding this void is a significant engineering challenge. Human jaws exert up to 200 pounds of pressure during a heavy bite, and a hollow tooth will shatter under that mechanical stress. While the tooth is now biologically safe, it remains mechanically useless until the void is filled and the structure is reinforced. This 1891 photograph of a dental office illustrates how long we have been struggling with this exact problem. For over 150 years, the objective has been to find a material that can withstand the environment of the mouth. Early solutions were rudimentary. Dentists relied on heavy metal tools and crude mechanical patches to plug these gaps, effectively using hardware store logic to fix biological problems. The long-term standard was dental amalgam, a durable, silver-colored mixture of metals like silver, tin, and copper. Amalgam's primary limitation is that metal cannot chemically bond to a tooth. To keep a metal filling in place, the dentist has to shave away healthy enamel to create an undercut, a shape wider at the bottom than the top that physically wedges the metal block into the tooth. Modern dentistry has shifted towards composite resin. This material matches the color of the tooth and functions through chemical adhesion rather than just mechanical wedging. Because this resin forms microscopic bonds with the tooth surface, the dentist only needs to remove the decayed tissue. The material supports the remaining tooth structure from the inside out, preserving more of the natural enamel. Material science has moved the practice of dentistry away from simply hammering a metal plug into a hole toward the reconstruction of the tooth's original form. To complete the repair, the resin is shaped to match the patient's bite and exposed to a specific wavelength of ultraviolet light. This causes the material to harden instantly, sealing the inner tooth against future bacteria. In under an hour, the tooth's appearance and function are restored. The structural breach is closed, and the pain is gone. Even with these materials, a dental filling is not a permanent, invincible shield. Fillings face constant mechanical wear from chewing and grinding. Over 5 to 10 years, they can chip, wear down, or pull away from the tooth, eventually requiring replacement. The most effective long-term strategy is preventative maintenance. Consistent soft brushing, routine daily flossing, and a lower sugar intake keep the mouth's pH balanced, allowing your saliva to protect the enamel before it ever fails. A dental filling provides a functional repair for a damaged tooth. However, The most lasting victory is maintaining an environment where your natural enamel never needs to be replaced.